In the last two videos, we've talked about how to find the inverse of a matrix, either a 2 by 2 matrix or a larger matrix where we have to go through a Gauss-Jordan kind of process. In this video, I want to talk about how to use the inverse of a matrix to solve a linear system. So here's a couple of quick facts about using matrices to solve a linear system. First, if the matrix that we're working with, the coefficient matrix A, is invertible, then that means that there exists a unique solution. So if you're able to find the inverse of a matrix, you're going to have a unique solution. If it's not invertible, then either there is no solution or there are infinitely many solutions. Let's do an example to see how this works. So here we have a system of two equations and two variables. If we write this down as a matrix equation, we're going to start with a matrix A of coefficients. So A is going to be the coefficient matrix, so that's 2, 2, minus 5, and 3. We'll have the constants matrix, so that's the right-hand side vector. That'll have 4 and 12 in it. And then our equation is going to look like ax equals b, where x is our variable vector, x1, x2. To use the inverse of a matrix to solve a linear system, of course, the first thing to do is find that matrix. So we're going to find A inverse, and since this is a 2 by 2, we can use that syntactical formula and just write down what the inverse is. So remember, we're going to have 1 over 2 times 3 minus 2 times negative 5. So that would be 2 times 3 is 6, minus negative 5 is a plus 10. And then we're going to multiply that number by the matrix we get when we swap the diagonal entries of A and negate the off-diagonal entries. So simplifying this a little bit, we have 3/16 minus 1/8, 5/16, and 1/8. Now we can use this to solve our system because it exists, so we know that there's a unique solution. And if we multiply both sides of our equation by A inverse, we know that A times A inverse, this is just equal to the identity matrix, in this case the 2 by 2 identity matrix. And the identity matrix times the vector x, that's just equal to x. So this is the quantity now that we want to compute, the solution vector x. So we're going to compute A inverse times B by doing this the usual way. So we'll have 4 times 3/16 minus 12 times 1/8. So 4 times 3/16, that's 3/4, plus 12 times negative 1/8. So that's negative 3/2. The bottom one, let's see, we're going to have 5 times 4, so that's 20/16, so that's 5/4, plus, again, 12 times 1/8, so that's plus 3/2. So in the end, we get that our solution vector is equal to negative 3/4, 11/4. And that's it, we're all done. To check, you just plug negative 3/4 in for x1 and 11/4 in for x2, and then check to see if these equations are satisfied. Let's see now a bigger example, a 3 by 3, and we can practice computing that inverse as well. Okay, so this is a 3 by 3 example. Let's write down our linear system as a matrix equation. So we'll have our coefficient matrix A. It will be 1, 1, 1, 2, minus 1, 0, and let's see, watch the indices here, right? That'll be a 1, minus 2, and a 0. Our B vector is just 1, 3, 5. And of course, our variable vector is, again, the x1, x2, x3. And we're looking to solve ax equals b. To solve this equation using an inverse, of course, we first have to find A inverse. And the process for that is to set up an augmented like matrix where we have A on one side and the identity matrix on the other side, and execute Gauss-Jordan to get the matrix on the left-hand side into reduced echelon form. And once we've achieved that, the matrix on the right-hand side will be the inverse. So we'll start by subtracting two row 1s from row 2 so that we can clear out that 2. This. And now we're going to move on to the next pivot. We'll start trying to clear out this entry below the -3. So we'll have row 3 minus 2/3 row 2. And once we've executed that, we'll have this. And now we're at the scaling phase of Gauss-Jordan. So we'll do nothing to row 1, but we're going to multiply row 2 by -1/3. And we're going to multiply row 3 by 3/7. Once we've done the scaling, now we start with the backwards elimination. So we'll use these row operations, and then we will get this. And finally, just have one more thing we need to clear out here, right? We need to do, still in the backwards elimination phase, we need to clear this out. So we'll do a row 1 minus row 2. And this is going to give us in the end. And now we are finished with our elimination and have this matrix on the right-hand side. And this is our inverse. So now we can take A inverse and multiply it by B, and we'll get our solution vector. Because remember, if AX equals B, multiply on both sides by A inverse, and we're left with X equals A inverse B. So now we're going to compute that. And I'll show you a little trick that I like to do. All these entries have the same denominator. I'm going to pull that denominator out as a scalar. So I'm going to write A inverse as 1/7 times 1, 3, minus 1, 2, minus 1, minus 2, and 4, minus 2, 3. See what I did there? Now I don't have to deal with fractions anymore, at least not for a bit. So I need to compute A inverse times B to get X. So this is telling me that X is equal to the scalar 1/7 times this matrix 1, 3, minus 1, 2, minus 1, minus 2, and 4, minus 2, 3. And since, let's see, vector B is 1, 3, 5, we just need to compute this product and we'll be all set. We'll have the solution to our linear system. And here it is. And if we bring the scalar back inside, that's what we get. All right, that's how we use inverse matrices to solve linear systems. And I just want to remark one more time, if the matrix is invertible so that you can actually go through this process and get an inverse matrix, then the solution will be unique and you won't have to worry about any kind of general form anything. But if it's the case that it's not invertible, then you'll either have infinitely many solutions or no solution. And the only way to tell is to go through the Gauss-Jordan algorithm and get your system into echelon form or reduced echelon form. Okay, that's it for this time. And next we're going to talk about some other tricks that we can do with the Gauss-Jordan algorithm.